Hello dear students, in today's class we are going to see few examples of subrings. As explained previously in the subring criteria, if you are having a ring and if you are having some non-empty subset of R, it is said to be a subring if these two conditions are satisfied. The first one is for all AB belongs to S, naturally AB should be again in S and A minus B should be also in S. So this second condition is taking care of the additive properties and this first condition is taking care of the multiplicative properties that are there in the definition of a ring. Now let us begin with the proof, with the solution rather. Now a ring is given to us which is nothing but M2 of R and S is given, and the question is check whether S is a subring of R or not. Now since the question is to check, we are supposed to one by one check all the conditions starting from the non-emptiness subset, and this two conditions we will try to prove. If we are able to prove these two conditions, then it will be a subring, and if we are unable to prove it, then we will give some counter example. Now first of all, non-emptiness. Now the question is why this S is non-empty. In order to prove that, we are supposed to understand what exactly S is. So S is actually collection of again 2 by 2 matrices with real entries. As you can see, what is our R? R is also a collection of 2 by 2 matrices with real entries, but there is one extra condition on elements of S, that is nothing but the sum of A and C should be equal to the sum of B and D. If this happens, then and then only certain 2 by 2 matrix will be in S. For example, let us say I am having, let us say this 1, 2, 3, 4. Now it is a 2 by 2 matrix, no doubt about that. Now the entries are also real. So this element is actually of R. In our case, the notation is M2 of R, right? R stands for M2 of R. Now the question is whether this element belongs to yes or not. So if you add them, 1 plus 3, that is 4, and if you add 2 and 4, that is 6. So you can see that 4 is not equal to 6 here. So our conclusion is that this element is not in yes, because what should happen? The sum of these two elements should be equal to sum of these two elements. So which is the element that you know in which this happens, right? And as I told you, our natural choice is going to be the identity element of R. So clearly I will say this 0, 0, 0, 0 belongs to S. As said that nothing is clearly in mathematics, there is some reason for it. As you can see, this 0 plus 0 is 0, and again this 0 plus 0 is also 0. Both are equal, and therefore this belongs to S is there, and therefore we will conclude that S is non-empty. Now subset ला काही issue नहीं है, there is no issue for the subset. So this S is a subset of R. Now directly we will move towards proving our both the properties, but in order to prove that properties we need two arbitrary elements of S. We will call them as A1 and A2, actually capital A1 and A2 because we are dealing with matrices. So I will say let A1 is equal to A1 B1 C1 D1 comma A2 is equal to A2 B2 C2 and D2 belongs to S be any elements. Now since A1 and A2 are elements of S, so what will happen? The sum of A1 and C1 will be equal to sum of B1 and D1, and similarly for this sum of A2 and C2 will be equal to sum of B2 and D2. So I will say this implies A1 plus C1 is equal to B1 plus D1 and A2 plus C2 is equal to B2 plus D2. Let us call it as sum 1. Now moving towards proving the first condition. So naturally I am going to consider the multiplication of these two arbitrary elements that we have taken from S. So I will say consider A1 multiplied by A2 and let us see what we get. So this is equal to my A1 is okay. So that is what we get after multiplying this A1 and A2. Now there is no doubt about that this is a 2 by 2 matrix, right, with real entries. No doubt about that, because all AIs and BIs, CIs and DIs are real numbers. Now only the question is whether the sum of these two entries is equal to sum of these two entries. If anyhow we are able to show this, then we will conclude that this A1 multiplied by A2 will actually be a member of yes. So indirectly now we have to check, I will say to check, okay, whether this, right, this is the addition of these two numbers is equal to addition of these two numbers. So let us consider LHS and let us try to simplify and let us try to prove whether we get the right hand side or not. So I will say consider LHS. Now if you observe properly, this entry and this entry has A2 in common, that can be taken out. Remember A2 is on the right. So this is A1 plus C1, outside is A2, plus similarly this term and this term has C2 in common. So we will take it out. Which property we are using? Multiplication distributes over addition. That property of ring we are using here. Yes. Now if we observe right hand side properly, what are the terms that are there? We are having C1, we are having A1, and then we are having B1, we are having D1, what else we are having? And we are having B2, D2, yeah, okay, that is what we have. So we have to keep in mind these things, because actually we have to show that the value of this is nothing but the right hand side. Now from 1 what we have? From 1 we actually have the value of B1 plus D1, that is A1 plus C1. So this we will use. So this is equal to actually A1 plus C1 outside A2 plus A1 plus C1 outside C2. This is using 1. Now again this A1 plus C1 can be taken common. So A1 plus C1. So what is left out inside? A2 plus C2. Now again, what is the value of A2 plus C2? So the value of A2 plus C2 is B2 plus D2, that can be used. So this is equal to A1 plus C1 and B2 plus D2. Now let us take multiplication of this and let us see what we get. This is the one way to do it, or the other way around is ki simplify the right hand side also, and let us see what is the value of RHS, and if LHS and RHS both are same, then we are through, right? I think that is the easiest way to do it. So I will consider the right hand side here and we will simplify that as well, and we will meet after simplification. So I have simplified the right hand side also. As you can see, in this term and in this term we are having B2 in common, that has been taken out. In this term D2 has been taken out. Again I have used the value of B1 plus D1 from 1, that is A1 plus C1, and by taking A1 plus C1 out I got exactly this. And you can see that from 2 and 3 what we have is कि LHS is equal to RHS. This is the only key step in this example. If you are able to do this, then you can easily prove that it is a subring, right? Right now we have not proved it, but there is one more condition that we have to check as well. Keep that in mind. Therefore, I'll say from 2 and 3 LHS is equal to RHS, and therefore this A1 A2 is a member of yes. Now we will move towards proving the second condition, that is A1 minus A2 should be a member of S. Then we can definitely say that this S is a subring. So I'll consider A1 minus A2 now, which is equal to, what was our value of A1? A1 B1 C1 D1 minus A2 B2 C2 and D2, which is equal to A1 minus A2 B1 minus B2 C1 minus C2 and D1 minus D2. Now again the logic is same. In order to show that this A1 minus A2 is a member of S, we have to show that the sum of these two is exactly equal to sum of these two. So I'll say to check this A1 minus A2 plus C1 minus C2 is equal to B1 minus B2 plus D1 minus D2. So I'll consider LHS, which is actually further equal to, so A1 plus C1 by simple calculations, A2 plus C2, which is equal to, but what is my value of A1 plus C1 from 1? As you can see, A1 plus C1 is B1 plus D1 and A2 plus C2 is B2 plus D2. So just use that value. Again by simplifying, one can see that this is equal to B1 minus B2 plus D1 minus D2, and that is nothing but our, thus okay, A1 minus A2 belongs to S. Now we have proved both the conditions of subring here, and therefore we can conclude that S is a subring of R. Now let us see the next example of a subring. So the question is same, we have to check whether S is a subring of M2 of R or not. So the ring R is again same as the previous example, M2 of R. It is a collection of 2 by 2 matrices with entries from R, thus it is called as M2 of R. Now again set S is given to us. Again it is a collection of 2 by 2 matrices with real entries, so no doubt it is clearly a subset of R. But what is the special property satisfied by elements of S? As you can see, the diagonal elements should be equal and the non-diagonal element should be also equal. I mean, if you are having certain type of element, let us say 1, 2, 3, 4, this element will not be in S because these two elements are different and these two are also different. So let us start by verifying the first property of non-emptiness. So why this S will be non-empty? As 0, 0, 0, 0 belongs to S, therefore S is non-empty. Now why does it belong to S? Again we can see that the diagonal elements are same and as well as the non-diagonal elements are same, therefore it belongs to S and S is non-empty. Clearly this is a subset of R, no issues with that. Now directly we will move towards proving the two properties of a subring. So in order to check whether the two properties holds or not, remember the question is to check whether a subring or not, right? So in order to check that, we are supposed to take two arbitrary elements of S. So again same notations, A1, B1, B1 and A1. Remember diagonal we have to take same as well as non-diagonal also we have to take same, and A2 to be A2, B2, B2 and A2 belongs to S be any elements. Now the first condition is regarding the multiplication. So we have to check whether A1 A2 belongs to S or not. For that purpose I will consider A1 multiplied by A2, which is equal to A1 B1 B1 A1, just putting the values of A1 and A2 here. Now I will multiply them together. Now after taking the multiplication, we can observe that these two elements are same, right? Because this is A1 A2 plus B1 A2. This is also A1 A2 plus B1 B2. They don't look same right now because the first term is A1 A2 here. But we know a beautiful property of rings that plus is always commutative, so we can swipe the positions. So that is not an issue at all. But remember, this order also matters sometimes in rings. So here it is B1 B2, here it is also B1 B2, but in some cases it may happen that it is B2 B1. Then in that case we cannot say whether these two are equal or not, isn't it? Because B1 B2 is here and here it is B2 B1. So for this to be equal, in that case the multiplication should be also commutative, isn't it? Okay, remember that is not the property of a ring, right? That doesn't come under the 7 properties. Okay, but no issues in this case, these two are equal. What about these two now? Now as you can see, it is A1 B2 here, A1 B2, same term. Order of A1 B2 is also same. B1 A2, B1 A2, same thing. Now plus is commutative, so we can just swap the positions. So this can be written as, the reason is plus is commutative in R. Therefore it belongs to yes, not an issue. Now moving towards the next property, that is we will consider now A1 minus A2, and this property is satisfied. If this property is satisfied, then we can definitely conclude that this S is a subring of R. So this is very straightforward and simple. These two elements are equal, these two elements are equal, therefore it belongs to yes. So both the properties are true. A1 A2 also belongs to S and A1 minus A2 also belongs to S. Thus we have concluded that this S is a subring of R. Now moving towards the next one, so I leave this example for homework, I leave it to you. Now what is the difference between the previous examples and this one? Now here ring is not M2 of R, it is M2 of Q, meaning it is again collection of 2 by 2 matrices, but the entries are rational numbers now, right? They are not real numbers. So this is the first change. The second change is, try to understand S now. S is again collection of 2 by 2 matrices, not an issue. But how are the entries? So the diagonal entries are exactly same, but the non-diagonal entries are not same. If it is B here, it should be 2B, right? I mean, suppose here it is 2, then it should be 4 here, right? And these two entries should be same. If such type of a number is there, then and then only this number will belong to S, otherwise not. But remember that this A and B are rationals again, so no issues. Clearly it is a subset of R, right? Again, in order to show it is non-empty, we can use the identity element and we can try to check that true properties, which I leave it to you. So we'll stop here. Thank you.